Hello and welcome to this lecture. In this lecture, we will talk about the successive cancellation decoder for polar codes. In fact, so far we have seen for n equals 2 and n equals 4, okay, so two small cases where we saw how the message passing happens on the binary tree. And what I will do in this lecture is generalize that to an arbitrary block length and general binary tree and show you how the message passing happens, what are the steps, etc. And after that we will do coding in MATLAB for that successive cancellation decoder. Okay, so you will see the steps in the decoder are quite simple and things also work out quite well, surprisingly. Okay, so let's get started. The setup is shown in the slide. We have the bits u1 to un coming into the polarization kernel Gn. Now remember, some of these UIs are frozen positions, some are message. Okay, so some frozen and some message. Okay, so that depends on the reliability sequence and the rate you want to transmit, etc. And once you send it through the polarization kernel, you get the symbols that you want to bits that you have to transmit, bits of the code word. You do BPSK, which is 0 to +1, 1 to -1. Okay, and then you do noise gets added on the channel, and then you receive R1 through Rn. Okay, so this is the received vector, and the goal, of course, is to go from the received vectors to the u's. Okay, once you find the u, you're done. Okay, so we saw all this, and how do you set it up in general is the question. Okay, so we saw that polar successive cancellation decoding involves passing messages on the binary tree, and every node in the binary tree is supposed to do some operations. We saw before that every node receives some beliefs from the top, from its parent. Okay, and then it first sends something to its left child, and then receives after it receives decisions from the left child, it sends some beliefs to the right child, and once it receives decision bits from the right child, it combines the two and sends them up back to the parent. Okay, so these are the three different operations the node has to do. So I'm going to write down that in a general way now. Okay, so far we saw it only for a specific example. We saw that sometimes the node has to deal with multiple incoming messages, not just 2, it could be 4 or 8 or something, and then how do you write it up in general? That I will do in the next slide. So that's what is shown here. So what are the operations in an interior node? So now what is an interior node? Any node which is not a leaf in a binary tree is an interior node. So the interior node will always have this kind of a setup. There will be 3 different steps or operations it has to do. I'm going to call the first one as L, okay, because it involves sending beliefs to the left child. The second one is R, because it involves sending something to the right child, and the third one is U, which you can think of as up. It involves sending messages back to the parent. Okay, so let's have some notation. First is this m is 2 power small m. Okay, the m can vary now, and the interior node will receive a set of beliefs. So these are beliefs. Okay, L1 through Lm, m beliefs it will get. Okay, you can organize that in a vector. You can think of it as a vector, and this is what is received by the interior node. Okay, so some interior node, it receives m incoming beliefs. Okay, in step L, which is sending it to the left child, what it does is it does min sum. Okay, this is min sum. Okay, but it does min sum in a particular way. So you see what it does min sum on. It does actually vectors. There are 2 vectors. It divides the vector L into 2. Okay, the first half. This is the first half of the vector. This is the second half of the vector, right? You can see the indices here. The indices go from 1 to m by 2, and then this goes from m by 2 plus 1 all the way up to m. So it divides it into 2, first half and the second half, and it does min sum. F represents min sum coordinate wise. Okay, so here is what I have done here. So if you have 2 vectors here of the same length, okay, and when you do min sum f on the 2 vectors, I simply apply the min sum coordinate wise. Okay, so I apply it coordinate wise. Okay, and that's what happens there on the node also. Okay, so the step L, the node takes its m incoming messages and splits it into 2 and applies min sum coordinate wise. Okay, So L1 and Lm by 2 plus 1, L2 and Lm by 2 plus 2, like that. Okay, so that's how it does. So it gets m by 2 values, m by 2 beliefs that it will send to the child. Okay, and the child will do whatever it has to do. It will again repeat some process like this. But as far as this node is concerned, it has finished the first operation, step L, which is sending m by 2 values. It got m beliefs in, it processes it using minsum and sends m by 2 values to the left child. Okay, so that's done. Now the next time this node comes into operation, it will receive something from the left child. Okay, so this is from left child. I have not shown that node here, but there is a node there which sends m by 2 bits. Okay, so when the left child is done finishing all the processing, it will send the bits back to its parent, and that is the step here. So once that happens, the same node gets activated once again. Okay, so it has to do the next step, which is step R. Okay, in step R, what it does is it does the G operation. Okay, so you remember the G operation. G was the repetition code sort of operation. Once again, the L is split into two parts, the first half and the second half, and then these decisions are also used, and together this G operation is done, and you compute m by 2 values. How is this done? If you have two vectors here, this is vectors of beliefs, and this is a binary vector. Okay, so this is the decision here. Okay, so I think this is there's something missing here. So this is a binary vector, that is that decision that's being received here. In the first step, you do G of A1, B1, C1. Here G of A2, B2, C2, and here you do G of AB, BB, CP. Okay, so you basically do coordinate wise, you apply the G operation. Okay, coordinate wise. We have seen this G operation before. It's either R2 plus R1 or R2 minus R1, depending on whether or not the bit is 0 or 1. Okay, so that's what is done here. So this is the repetition code. I'll put it within quotes. It could be repetition or it could be the complement of repetition. So based on that, it does this R2 plus R1 or R2 minus R1. Okay, so this is a simple enough computation. You can see what it has to happen. There are m values. The m by 2 bits coming in, there are m values here, there are m beliefs here, right? The same L is here on this side. You should retain the same L. L1, L2, Lm is still here. You use these beliefs that were incoming in the node, and then once you get some decisions from the left child, you combine the two using this function G and send it to the right child. Okay, so that is step R. Okay, so that concludes step R. Okay, so now the node can be quiet now. It doesn't have anything to do till it receives something back from the right child also. Okay, so this is what comes back from the right child. The right child has finished all it has to do, and it has sent back the decisions back to its parent. So this node is getting back something from the right child. So you remember, it already had u1 hat from the left child. It is getting u2 hat from the right child. Remember, these two u1 and u2 are now m by 2 bits each. They are not single bits. This is m by 2 bits. In general, we are looking at it. And what will the node do? It has to do step U once it has received incoming decisions from both the left child and right child. Once it has received that, it can do the step U, in which it does u1 hat plus u2 hat and u2 hat, which is m bits, and sends it back up to the parent. Okay, so we saw this also. This is how the operations go. So once again, to summarize, there are three operations in the interior node: step L, step R, step U. Okay, the moment the node receives any belief from its parent, it will do step L, okay, which is minsum, coordinate wise, splitting the beliefs into two. Okay, and then once it receives decisions from the left child, it will do the G operation, combining its incoming beliefs, again divided into two, along with the decisions in the G operation in the repetition code format, and then send it back to the right child. And it will wait for the right child to get back its decisions. Once the right child gets back its decision, it will do the combination and do the step U, in which it will compute what it needs to send back to its parent. Okay, so this goes to parent. This came from parent. Okay, so hopefully this is clear. These are the three different operations an interior node has to do. Okay, this is how it works. Okay, so what about a leaf node? Now a leaf node doesn't have any children, right? So, and it is just one bit. Okay, so when it receives any belief, it will receive only one belief, and that is a belief for itself. right? It receives a belief for itself. Okay, so now the leaf could be in two different situations. The ith node, this is the ith node, this is the ith node, ith leaf node. Now this ith position may be frozen or may be message. Okay, so that's the important thing here to take care of. If the ith position is frozen, then your decision ui hat will always be 0. Okay, so in fact in this case L of ui is sort of ignored. Okay, I'll say for now. Later on you will see we will figure out a way to use it, but for now it is ignored. Okay, if it's frozen. Okay, if it is not frozen, of course L of ui plays an important role. It is the soft information for ui, which is actually a message bit. So if it's greater than 0, you decide that ui hat is 0. If it's less than 0, you decide ui hat is 1. Okay, so this is the threshold decision. Okay, so that's the story here. So the leaf node is sort of simple. It gets one belief whenever it has to keep waiting till it gets its first belief. Since it's till it gets its belief, once the belief comes in, it's going to either use it or not use it, depending on whether it was frozen or not. If it was frozen, it's going to ignore and always send back a ui hat is 0. If it's not frozen, it's going to use that belief, use thresholding, make a decision and send back that decision. Okay, so that's what happens in the leaf node. Okay, so we've seen now what happens in the interior node, what happens in the leaf node, and now it's just an easy process to put everything together and get the overall decoder. Okay, so I'm going to describe the steps in the decoder. The decoder works in a certain sequence. You remember there's a binary tree, there's always a root. The main top node is called the root. So you start at the root. Okay, and every node you do the following steps. The steps are always the same. Okay, if you are not a leaf, if the node is not a leaf, for instance the root is not a leaf. Okay, so any other node, interior node which has children, it's not a leaf. Okay, if you're not a leaf, then you have to do the following things. Okay, you first do step L and then you go to the left child. What do I mean by to the left child? Once the beliefs are given to the left child, the left child becomes activated. Okay, and the left child will do whatever it has to do. Okay, so at every node, when it is activated, it has to do the following. Activated meaning when it receives beliefs. Okay, if it doesn't receive any belief, it can be quiet. There's nothing much for it has to do. Once it receives beliefs from its parents, it has to do the following. It will do step L and it will pass on control to its left child. Okay, and when will it get back control? When will it be activated again? When it receives decisions from the left child. When it does, it will do step R and it will go to the right child. Okay, and the control will be given to the right child. So after that it can relax. There's nothing much to do. After that it can wait for the right child to get back its decision. Once the decisions come back from the right child, it does the step U and it goes to the parent. It hands over control to the parent and it's done. Okay, so it's very, very simple operation for the node. It's very well defined and clear. Okay, what about the leaf? The leaf, whenever it receives its belief, it will check whether it's frozen or not. And frozen, send back 0. Not frozen, make a decision using threshold, send back the bit and transfer the control back to its parent. Okay, so this is the message passing sequence. It's a definite way in which it happens. It's not everything doesn't work in parallel. Very different from the LDPC decoder in that fashion. You remember the LDPC decoder on the Tanagraph, everything was working in parallel. Here it doesn't work like that. It works in a certain sequence, and there is a good reason for it. You remember the bit channels are they are ordered in quality. There is a reliability sequence. There are very bad channels, very good channels. You want to go from bad to good in some sense, and there are enough frozen things in the middle to make sure that you don't get diverted too much and may end up making mistakes. Okay, so this is the summary. Let's see one example, a very small example, where we'll follow through the operations. I'll indicate what the sequence of operations are. Okay, so this is the received values from the channel. Okay, I'm calling it R16. This is, I think, a 16,10 code. Okay, you can see the frozen positions here. Wherever I put 0, it's frozen. This is also frozen. The remaining positions are message bits. Okay, so what happens first? The root receives its incoming beliefs, and this is the first operation. So this number 1 indicates the sequence of the operation, and this L indicates the step Okay, the step could be L or R or U also, and this is the belief. And this 8 of course indicates the size of the belief. Okay. So, initially there are 16 beliefs that the root receives from the channel, and when it does L in its first step from the sequence number 1 L, it goes to the left child, okay, and gives control to the left child, but it sends only 8 beliefs, right. It would have done a min sum to combine the incoming 16 into 8, it sends 8. And what does the left child do? So, this gets activated now and it will do this step. Okay, so, this is the second step that gets done. It will send to its left child, it will do the L step again. Next, the second operation that happens is L, okay, and but it will send only 4 beliefs, right. It got 8 beliefs, it will send 4 beliefs. And then what will this child do? This child gets activated now, okay. So, once this third child gets activated, it will do this step, okay, which is again an L. Okay, remember, whenever a node gets activated, it always does L first. Okay, so it does L, then 4 beliefs become 2 beliefs, and then this node gets activated, and the fourth step it will do L again, and now you have a leaf node. It just receives a single belief and it's actually frozen, so it will send back 0. Okay, so what I have not shown here is the U step. Okay, I have not shown the U step at all. I have just shown the L and the R just to keep the picture free of clutter, and you can imagine the decisions and the U steps coming in, right. So, this will be a 0 that goes up here, okay, and then this node will do the fifth sequence in the sequence. After 4 you have 5, fifth will be an R. Okay, the first time you will get an R. Okay, so this node will do an R now, step R, which will be again 1 belief, and this will send back just 0. Okay, so because it's a frozen bit, so it sends back 0. You will have a U step here, okay, which I have not shown. Okay, after this you will have a U step, and then you have this gate. Okay, the next step is the number 6, which is the R. Okay, after you have the U, you have the R, and then this is the 7th step, which is L, and then anyway it's frozen, you get 0. This is the 8th step, okay, and then this will send back 0 again because it's frozen, and then this will do a U. Okay, so the U's I am not showing explicitly to avoid some clutter. So, U will happen here. So, both U's have happened here. So, this node can now do a U. Okay, this node at this level will do a U, and then you are ready to do an R. Okay, so the R happens after that. The 9th, this node will do an R because it has received its message from the left child. Once it receives the decisions from the left child, it will do the R. Okay, and then you do the L again, and then the L again, then the decision 0 will come, and then you do the R. Here you will get a non-trivial decision. Okay, it will not be 0, it will be whatever that decision is. Okay, so that will come up, and then once the 2 decisions are up, this will do a U, and then you do an R, then you do an L again. Okay, and then your decision comes up, and then you do this 15th, and then you do a thing, then you do the decision back up again, and then you do a U. Okay, U was done here, you will do a U here, then U done here, you will do a U here. Okay, once you do a U here, you can do the R. Okay, and you go down the right side. Okay, and then you continue. Okay, I have said just and so on. I am not going to repeat the whole thing, but this is what happens. Okay, so such things are called tree traversals. Okay, what is a traversal? Traversal is just going from one place to the other, and that's what you're doing on this tree, right? So you start from the root and you traverse the tree. Okay, so this kind of traversal has a name. It's a depth first traversal. Okay, so you go left first, down, and then keep going down and down and down and down on the left, and then only then you come back. Once you've gone to the leaf, you come back. So those kind of things are called depth first traversals. There are various ways to implement such traversals. We will do that soon enough, but this is what happens in a successive cancellation polar decoder. It's a very simple decoder to describe. You can picture it on the binary tree like this, and then you start from the root and then you traverse. Okay, traverse in a certain particular way. You do some operations when you go either left or right or up, and that's it. Whenever you have the leaf, you make a decision. Once all decisions are made, your decoder is complete. Remember, once you make this decision here, okay, so this will be the last decision you make, and you can stop your decoder. Okay, so at that point everything is done because all your message bits are decoded. Okay, if you want to, you can go back up and compute the code word. It's not really needed. That's the message bit. Once it's decoded, you're done. Okay, So this is complete polar decoder. This is for n equals 16. Even for n equals 1024, it's the same thing. Okay, so just that the picture becomes so much more complicated. It's difficult to draw it on a slide. On my own, definitely not. But you can imagine it's the same thing. Okay, so you do the same sequence of operations, and you'll get it to work. Okay. So this is the end of this lecture, and hopefully you got a clear idea of how the successive cancellation decoder works. Because in the next lecture, we're going to code this in MATLAB and then get it to work, hopefully. Okay. Thank you very much.